exercises with you, just because I know this happened a little while ago, and you have been studying for your test, was your focus, so you probably have not gone back and reviewed a lot of stuff for today. All right, so let's look at the function x to the fourth minus 2x squared plus 1. We want to decide if it's even or odd or neither. So how do we, anybody remember anything about how to do that?
Even is like,
yeah, even was reflecting about the y-axis. Yeah, odd reflects about the origin. Yeah, so how did we test this thing for symmetry? Let's see, what happens if I plug in a 2? If you plug 2 into f of x, what do you get?
16.
16 minus 8 plus 1, which is 9. Okay. What do you get when you plug in a negative 2?
16 minus 8 plus 1.
Okay, so what does it tell you that when you plug in, if you were graphing this thing, when you plug in positive 2, you get 9, and when you plug in negative 2, you get 9. So if I plot those 2 points, 2, 9, and negative 2, 9, what kind of symmetry do those 2 points have? Even symmetry. But just seeing those 2 points, does that mean that every single point on the graph will have even symmetry? No, so you have to actually check it for all x's. So let's see what happens. I know what I get when I plug in regular old x. That's my formula for regular old x. So I'm going to plug in a negative x, and I get negative x to the fourth minus 2 times negative x squared plus 1. What do you get when you take negative x to the fourth power? You get positive x to the fourth. Just leave it, please. What do you get when you square negative x? Just leave it, please. Yep. What do you get when you take negative x and square it? Everybody just lost concentration. X squared. Negative x times negative x is x squared. So I've got negative minus 2x squared, and then I've got plus 1. Does that formula look familiar? Yes. What does it look like? What I started with. That is exactly f of x. That's the algebraic definition of even symmetry. When you plug in a negative x, you get the same thing as when you plug in a positive x. So this is even. Okay, so before the test, we studied quadratic functions. Before the first test, we learned all about lines, right? So we know all about lines, we know all about quadratic functions. Those are two special cases of polynomials, degree 1 and degree 2. So the degree is just the highest power of x that you see in a function. Okay, so today we're going to study, expand our study of polynomials, and we're going to begin with the definition. So this definition looks kind of crazy, right? It's got all kinds of subscripts and variables and stuff. And then we'll just but it's not, you don't have to be able to interpret that. We're just going to jump to some examples. The number a sub n, that's just the coefficient on the highest power of x. That's called the leading coefficient. The number n is called the degree. And the very last thing, the number without any x next to it, is called the constant term. Okay, so here's some examples. I've got x cubed minus x squared minus 2x plus 4. What's its degree? Highest power of x you see? 3. Its leading term is the whole first term, the term that includes the highest power of x. So in this case, it's x cubed. What the leading coefficient is the coefficient that shows up in the leading term. In this case, it's a 1. And what's the constant term? 4. That's the number that just has no x on it. All right, we're going to leave this end behavior stuff until later. So now I've got this this polynomial 3/2 x to the 5th plus 5/2 x to the 4th minus 5/2 x cubed minus 5x squared. What's its degree? 5. That's the highest power on x. What's my leading term? Close. Yep, 3/2 x to the 5th. And my leading coefficient? 3/2. Constant term? 0. Yeah. There is no term that doesn't have an x in it, right? So you could just call it 0. 1 minus 2x minus 3x squared, what's the degree? 2. Yep, highest power of x is 2. What's my leading term? It's negative 3x squared. Yeah, it's not necessarily the first term that shows up. It's the term that includes the highest power of x. So leading coefficient would be negative 3. Constant term is 1. Ooh, here's a tricky one. Negative x squared times x plus 2 times x minus 2. Yeah, you got to distribute it out. So let's imagine multiplying it out. What's the degree going to be? Before we start doing all the multiplication, can you predict the degree? 4. How did you know that? Yeah. You've got x times an x squared will give you an x to the 4th. So my degree is going to be 4. So let's actually do the multiplication out just in case we couldn't see that. So I'm going to keep the negative x squared for now, and I'm going to FOIL the x plus 2, x minus 2, and you get x squared minus 4. And then distribute the x squared that's out front, and you get negative x to the 4th plus 4x squared. So I just simplified that to put it in polynomial form. All right, what's my leading term? Negative x to the 4th. What is my leading coefficient? Negative 1. And my constant term? 0. Good. All right, so you guys now have a lot of the important vocabulary about polynomials. All right, the next really important characteristic of a polynomial's graph is its end behavior. And the graphs of all polynomial functions will eventually rise or fall without bound. They eventually just go up to infinity or go down to infinity when you go way out to the right of the graph or way out to the left. So let's just look at a few examples and see if we can figure out when it goes up and when it goes down. And we're going to learn some new notation for describing going up and going down. So here are two linear functions. This one on the left, as you travel this graph moving to the left, it's falling, right? And as you travel this graph moving to the right, it's rising. So the way we describe that, this is called arrow notation. You would read this as x approaches negative infinity. That means you're moving left, right? Because x is left and right, and we're going towards negative infinity, so we're moving left. As you follow that graph to the left, f of x is falling, so that means that the y values are approaching negative infinity. So you read those arrows as approaches. And then underneath there, it says as x approaches positive infinity, that means as you move to the right, f of x approaches what? Positive infinity. The y values just go up. And then if I do the line on the right here, as x approaches negative infinity, meaning moving to the left, what's happening to my y values? They're going to infinity. And as x approaches negative infinity, meaning a moving left, what's happening to the y values? Oh yeah, I meant positive infinity. It'll be negative infinity. Thank you. Okay, so that's linear. One side will go to infinity, the other side will go to negative infinity. The side just depends on whether the graph has positive slope or negative slope. All right, what about quadratic functions, the next special kind of polynomial? For this graph on the left, whether you go to the right or the left, what happens to the y values? they all go up. So they're all going to go to positive infinity. If x approaches negative infinity, the y values go to infinity. As x approaches positive infinity, the y values also go to infinity. And then for this graph, when you go to the right and go to the left, the graph falls in both directions. So these are both negative infinity. And then here's a cubic. Just a random graph of an odd degree, of a third degree polynomial. As x approaches negative infinity, as I move to the left, what's happening to the y value of this graph? Negative infinity. And as I move to the right, it goes to positive infinity. And then it switches, right? For this picture on the right, it rises to the left, which means it goes to infinity, and falls to the right, goes to negative infinity. And here's a quartic function, which is a fourth degree polynomial. Here, both go up or both go down. As you go to the left or the right, you either approach positive infinity or negative infinity in both directions. Which one? This? Yeah, that's a negative infinity. So this quartic, as you go to the right or the left, the y values approach infinity because they're both pointing up. Right? And then the one on the right, as you go to the left or the right, the y values are going down to negative infinity. So maybe you saw the pattern here, right? When the degree was odd, like when it was 1 or 3, the ends do opposite things. One goes up and one goes down. When the degree was even, like 2 or 4, the end behavior did the same thing in both directions. Either they were both up or both down. So this is the conclusion about end behavior. Okay. It doesn't tell you anything about what happens in the middle, but it can tell you whether the graph rises right, rises left, falls right, or falls left. So you can always tell by looking at the degree, right? The degree tells you whether both arms are up or whether both arms are doing the same thing or the two arms are doing opposite things, right? Odd degree, you have opposite behavior. Even degree, same behavior. And then to decide which arm goes up and which arm goes down, when the leading coefficient is positive, it's the right arm up. When the leading coefficient is negative, it's the left arm up. Leading coefficient positive with even degree, both arms up. Negative with even degree, both arms down. All right, so let's go back to number 2, our examples, and fill in the end behavior in this table. So now we don't have pictures. We have to be able to figure it out just by looking at the formula. So my degree of this guy is 3, which means opposite behavior. One arm's up, one arm's down. The leading coefficient is 1, which is positive, right? So the important fact about this guy is that it's odd. And the important fact about this guy is that it's positive. So that means one arm's up, one arm's down. That's odd. And because it's positive, it means right arm up, right? So this is the end behavior. Right arm up, left arm down. So that means as x goes to negative infinity at the left, it's going to go down. And at the right, it's going to go up. How about this next one? What's its end behavior going to be? Mm-hmm. Leading coefficient is positive, the degree is odd, so it's going to be the same as the last one. Okay. How about the third example? Here my degree is even, so it's either going to be both arms up or both arms down. My leading coefficient is negative, which means both arms down. So that means that as x goes to negative infinity and as x goes to positive infinity, f of x, which is the way we describe the y values are both going to approach negative infinity. And the last one is the same. Yep, because we've got even degree, negative leading coefficient. Is that okay? So now if I give you a picture, you can describe its end behavior with arrow notation, or if I give you a formula for a polynomial, you can describe its end behavior with arrow notation. Okay, so now we know what happens at the far right and the far left of a polynomial graph. Now I want to look at the short run behavior. What happens in between? Okay, so one important thing that can happen before the long run behavior happens is that we could have zeros, right, which are x-intercepts. So the values of x for which f of x equals 0 are called zeros. So if I want to find the zeros of a function, I just set it equal to 0 and solve it. Okay. Any ideas on an approach we could take to solve this equation? A factor, yeah. Do these guys have a greatest common factor that I could factor out? X. And then I'd be left with x squared minus x minus 2. X squared minus x minus 2, does that factor? Yeah. So now I have x times x minus 2, x plus 1 equals 0. And then, because I'm multiplying three things together and I have an answer of 0, one of them has to be 0, right? Either x equals 0, or x minus 2 equals 0, or x plus 1 equals 0. And when I solve each of these equations, my zeros end up being, well, 0. That one's solved. X minus 2 equals 0. When you solve it, you get 2. And x plus 1 equals 0. When you solve it, you get negative 1. So there are my three zeros. So that's how there's a slight technical difference between zeros and x-intercepts. Zeros are just the x values where the function is 0. X-intercepts are points, right? So what point corresponds to an x-intercept, what point corresponds to a 0 of, say, 2? That's a y-intercept. 2, 0. 2, 0 is my x-intercept. 0 would be 0, 0. And negative 1, 0. So zeros and x-intercepts are like almost synonyms. They mean basically the same thing. Okay, so let's just pull up GeoGebra and look at a quick graph of x cubed minus x squared minus 2x and verify that it has these three zeros. Okay, so I graphed it, and it does look like it has x-intercepts at negative 1, at 0, and at 2. Those are the three that we found algebraically. And here's my formula. It's written over here. Show that. So I'm going to hide the graph for a second. Just look at that formula. What's its end behavior going to be? Opposite end behavior because it's odd degree. So which arm is up? The right arm is up, yeah. So the right arm is up because the leading coefficient's positive. So let's bring the graphics view back, and you can verify that. Right arm's up, left arm's down. Okay, so here's a couple of polynomials that I've graphed for you. They both have zeros at x equals 1, right? They both have x-intercepts at 1, 0. Okay. But those x-intercepts look significantly different, right? This is the graph of x minus 1 squared. So it's basically the graph of of x squared shifted right 1. So it's x minus 1 squared. So if I were to set x minus 1 squared equal to 0, x minus 1 squared means x minus 1 times x minus 1. And then you set each factor equal to 0, right? And you get x equals 1 as a solution to both equations. So we call that, we say that 1 is a real 0 with multiplicity of 2, because it actually shows up twice when we're solving for it. So we say it has multiplicity of 2. So that also, another way to recognize when you're going to have double multiplicity or triple multiplicity is by seeing that this factor is repeated. X minus 1 is repeated twice. So it's got multiplicity 2. All right, and then this guy, g of x on the right, this is g of x is x minus 1 cubed. So it's the graph of x cubed shifted right 1 unit. And so that means that if I was trying to find the x-intercepts here, or the zeros, I would take the function, set it equal to 0. But that means x minus 1 times x minus 1 times x minus 1 equals 0. So x minus 1 equals 0, or x minus 1 equals 0, or x minus 1 equals 0. And you end up getting x equals 1 3 different times. So we say that 1, the way we express the fact that you get 1 as a 0 3 different times, you say 1 is a real 0 with multiplicity of 3. And you could see that from the formula because that factor x minus 1, it happens 3 times. It's cubed. All right, so what is the big qualitative difference between this x-intercept on the left and this x-intercept on the right? Yeah. The multiplicity, yep. But graphically, what looks different in this picture than this picture? Yeah, so this one, it comes down to that x-intercept and hits it, and then turns around and goes back up, right? In this one, it comes to the x-intercept and then just passes right through it and keeps going the same way it was going before. Okay, so it turns out that this kind of a bounce off the axis is typical when you have an even multiplicity. Any even multiplicity. So this one has multiplicity 2. 2 is an even number. So you get that bounce off at the 0. And then this picture going right through the axis is typical when you have an odd multiplicity. So this one, the multiplicity was 3, so it actually goes right through the x-axis and continues on its way. So I have it summarized here. The multiplicity of a real 0 tells us about the graph's behavior near the x-intercept. When the multiplicity is even, the graph touches the x-axis and then bounces off. Right? If the multiplicity is odd, the graph crosses the x-axis. If the graph crosses the x-axis in a linear fashion, right? So if you look at this picture, zoom in on that x-intercept, does that look like a line going through the x-intercept? No, it's curvy, right? If it looks like a line, that means your multiplicity is 1. If it goes through but looks like a line, your multiplicity is 1. If it's curvy, right, if the graph flattens out or is curvy as it crosses the x-axis, the multiplicity has to be bigger than 1, like 3 in our example. All right, so if you want to find a multiplicity of a real 0, you have to be able to write your polynomial in totally factored form. You have to see how many times a factor appears to know how many times that 0 is going to appear. Okay, so I know this is going a little long, but I'm sorry. So now that we've explored the concepts of end behavior and zeros and their multiplicities, for polynomial functions, we can learn how to create a quick sketch of a polynomial function. Okay, so step 1 is look at the end behavior. Okay, so here's my function, x to the 4th minus 6x cubed plus 9x squared. So touchdown, yeah. It's got even degree, positive leading coefficient, both arms up. So you can even just draw yourself a little sketch of what the end behavior is going to look like if you don't want to use arrow notation. So we know the end behavior. X-intercepts you find by just setting the function equal to 0 and solving it. That's what we just did, right? So we factor it. What's my greatest common factor for these 3 terms? X squared. So I've got x squared times x squared minus 6x plus 9. And then that's got a factor to x minus 3 times x minus 3, or x minus 3 squared. And then you set each factor equal to 0. So you get x squared equals 0, or x minus 3 equals 0, or x minus 3 equals 0. So we have x equals 3, x equals 3. X squared equals 0 means that x is 0, but what's my multiplicity on this guy? 2, because it was squared. So this is multiplicity 2. And then x equals 3 showed up twice, so it has multiplicity 2, right? So x equals 0 is a 0 with multiplicity 2, and x equals 3 is a 0 of multiplicity 2. Step 3, find the y-intercept. In general, to find y-intercepts, you plug 0 in for x. So what's my y-intercept here? What's f of 0? 0, yep. All right, and then the last step is find out if there's any possible symmetry to help you graph the function. Because if it has some kind of symmetry, you only have to figure out what half of it looks like. The other half is a reflection. So let's see, if I plug a negative x in here, I get negative x to the 4th minus 6 times negative x cubed plus 9 times negative x squared. So that is positive x to the 4th. Negative x cubed means negative x times negative x times negative x, which would be negative x cubed. So I have a negative 6 times negative x cubed. That's positive 6x cubed plus 9x squared. Does that formula look familiar? Are you sure? Kind of, but does it look exactly like f of x? Yeah. So it's not f, right? It's not exactly the same as f. It's close. Is it exactly the same except every sign has changed? No, which means it's also not equal to the opposite of f of x. So it's got no symmetry. No symmetry. So now we just draw all the things we know about this graph. We know its end behavior, we know its zeros and their multiplicities. So we've got a 0 at 0 and at 3. And I know they're both even multiplicity. They both had multiplicity 2, which means that the graph is going to bounce off there. And I know my end behavior, once I get past my short run behavior of the zeros, it's touchdown. So from here, it's going to go up, and from here, it's going to go up. And I know I have to have bounce off at both of these zeros, so it's going to do something like that. And this is a qualitative picture. We have no idea how high that bump goes. Yeah, so you just connect it in the only way that using the information you have. So how high, right? We don't know, right? In calculus, you'll be able to figure out exactly where that peak is. But for now, we'll just draw a rough qualitative sketch of the general idea of what happens there. Okay, that's it. Now you can do some on your own.